So, heading energy of simple harmonic motion. So, best example you can take either simple pendulum or spring mass system. Let us say I will take spring mass system. As an example for simple harmonic oscillator. Okay. We know that the kinetic energy Ek, let us represent kinetic energy by Ek, which is basically half mv square. The energy possessed due to its velocity is called kinetic energy. Okay. As we know that half m, V is, in the beginning we proved that V is nothing but a omega cos omega t. Y is equal to a sin omega t. If I differentiate, we will get velocity a omega cos omega. Square it. So, the kinetic energy of simple harmonic oscillator is half m a square omega square cos square omega t. You can express in terms of displacement also. How? Kinetic energy Ek is equal to half m a square omega square. Cos square theta can witness. So, cos theta can witness root of 1 minus sin square theta. Cos square theta is 1 minus sin square theta. 1 minus, let us call as, here displacement we call it as x, downward direction. The displacement we call as x. 1 minus x square by a square. You may ask, how do you get this as well? Okay. X is equal to a sin omega t. X is equal to a sin omega t. Sin omega t is x by a. If I simplify this, I will get the kinetic energy is of m omega square a square minus x square. So, the kinetic energy is function of x square. That means, if I plot a graph, the kinetic energy versus displacement, it is a parabolic function like inverted parabola. At extreme position, that is when x is equal to either plus a or x is equal to minus a, that is extreme positions, the kinetic energy is 0 since velocity is 0, and kinetic energy is maximum at mean position x is equal to 0. Okay. So, kinetic energy is a function of x square with a parabola graph. Next, let us calculate what is the potential energy of this mass, which is in simple harmonic motion. We know that the displacement of simple harmonic oscillator x is equal to a sin omega t. I am assuming that it is starting from mean position. I am calling displacement as x. You can call either x or y, depends on your condition. So, x is equal to a sin omega t. Now, what is potential energy? How do you define a potential energy? Potential energy is the energy possessed due to its position. So, if I use potential energy also capacity to do the work, if I use dW is equal to f dx and total work is equal to integral of f is nothing but kx dx, work done in extending the spring by x is integral of kx dx. From x is equal to 0 to some value of x, if I integrate, I will get work done is equal to half kx square. The work done in extending the spring by x. This work is stored as elastic potential energy, that is potential energy we call as EP is of k x square. So, again the potential energy is directly proportional to square of the displacement. Again it is a parabola only. And what is the difference between this parabola and the earlier kinetic energy parabola is, it is exactly opposite sense. If I plot potential energy versus displacement, I will get a parabola like this. Okay. Look at here. Plus A the potential energy is maximum at extreme positions and minimum at mean positions, whereas kinetic energy is 0 or minimum at extreme positions, maximum at mean positions. Okay. If I superimpose that graph also here, okay, this graph is for kinetic energy, this graph is for potential energy. And one more thing important is, at any position of x, sum of these two energies is constant. Sum of potential energy and kinetic energy due to SHM remains constant. So, total energy doesn't vary with x, it remains constant. So, these are the graphs of energy of simple harmonic oscillator. So, now we will see what type of questions that may be asked regarding to the simple harmonic motion. Let us say little bit complicated. Take one simple condition. The two particles which are in SHM with same amplitude and time period, meeting at x is equal to a by 2 meeting at x is equal to a by 2. Okay. Imagine two particles are in SHM along the same line, let us say along x axis, but they are meeting at x is equal to a by 2, no doubt, but one is moving towards right, the other one is moving towards left, like this. Okay. What is the phase difference between these two particles? That is what they ask. What is the phase difference between these two particles? Okay. Now, this type of problems we can use a simple technique. Let us say a simple pendulum. Y is equal to 0 means phase is 0. Y is equal to a by 2. What is the phase? Y is equal to a sin theta. When y is equal to a by 2 means theta is 30. The phase of this is 30 degrees or pi by 6 radians. Y is equal to 0, y is equal to 30. In extreme position, we know that phase is again 90 degrees or pi by 2 radians. Look at this, 0, 30, 90. The y is equal to a by 2, theta is 30, y is equal to a, theta is 90. Now look at what is the condition given. They are meeting at y is equal to a by 2. Okay. Imagine this bob has to come back to the same position. What must be the phase change? 30 to 90, 60 degrees it has to go. Again to come back to the same position, again 60 degrees it has to go. Okay. Here degrees means phase. Okay. From here to here 60, from here to here 60, total phase difference is 120 degrees or pi by 3 radians. So, this conceptual way you have to solve it. We can avoid more mathematical, conceptual way you can work it out like this. So, let us go back to the other branches of physics where the simple harmonic motion is involved. This is the one where we come across almost all topics of physics like sound, electromagnetism, and fluid dynamics. Let us say a cylinder is floating in liquid. A cylinder where upthrust is balanced by its weight. Its upthrust balances the weight, it reaches equilibrium position. Okay. Now, just push a small x, press it and leave it, then it executes simple harmonic motion. Okay. Let us find out what is the frequency of this simple harmonic motion. As we know that for any simple harmonic motion, we have to prove force is proportional to displacement and directed opposite to displacement. When you compress by x, the restoring force developed is F. Then how do you calculate this restoring force? Then you have to go back to our Archimedes principle. Upthrust is equal to the weight of the liquid displaced by the body. Upthrust is equal to the weight of the liquid displaced by the body. If A is the area of cross section of this cylinder, so upthrust always VL dl G. Upthrust is equal to VL dl G. What is VL? Volume of the liquid displaced by the body. dl is density of liquid. G is the acceleration due to gravity. When I am compressing down, the upthrust is acting up, right, minus I. Upthrust try to push back this one. So, since F is equal to ma, let us write the restoring force is ma, and then what is this VDL? This VDL I can write area of cross section into length is volume, area of cross section to length, that is extra upthrust, into dl into G, right, minus I. So, the acceleration A is equal to minus A dl G by m, which is a constant, into x. So, A is equal to minus some constant into x, which is the condition for simple harmonic motion, and equate this A is equal to minus omega square x. From that, find out omega and find out time period. So, like that we can connect almost many cases to simple harmonic motion in different branches of physics.